This video is on hydrates, and as you might guess, the word hydrate has something to do with water. So, what is a hydrate? Well, technically it is a chemical with water molecules attached. So, when students hear that, they automatically think liquid, okay? And hydrates are not liquids. Hydrates, they are solids. So a hydrate, and I'll show you this in class, will look like a powder, just like any other chemical we work with. So just like sodium hydroxide or calcium chloride or whatnot, looks like a powder. Or pellets or whatever you want to call it. Hydrates resemble those chemicals. They look very similar. So students hear hydrates, they think liquid. No, not true. They're actually solids, but they have H2Os attached to their chemical formula, attached to their structure. So hydrates are really easy to recognize in formulas because they look really weird. So this is an example of a hydrate. And they have a dot and then so many waters attached. Okay, so this is unlike anything you've ever seen before. And so this is a hydrate. You can recognize it because of the dot H2O. And that number in front can change, and that's what we're going to talk about later. That's the ratio of how many waters there are. Okay, so hydrates can easily be dehydrated using heat, and we will do this as a lab. So we're going to write a reaction in a minute. I'll show you a dehydration reaction, and then we'll further talk about how we can use that to do hydrate calculations. Okay, so then if a hydrate has H2O molecules as part of its formula, what's an anhydrate? Okay, well, an anhydrate is what is left over after the hydrate has been dehydrated. And anhydrates are also solids. Okay, so let's talk about a dehydration reaction. So we'll use my first example of the copper sulfate hydrate. Okay, so if we heat this, and of course that's the symbol for heat, we're going to remove the water, we're going to dehydrate it. So you would have the ionic substance left, okay, as a solid. And the 5, in this case, waters, okay, would be in the gas form because you have dehydrated it and you've removed the water as steam, okay, or water vapor. So hydrates will always weigh more than what your anhydrate weighs because the water is removed. Okay, so this is the hydrate. And this would be the anhydrate. And then, of course, water. Okay, so you can dehydrate a hydrate by heating it. You can also rehydrate an anhydrate by adding some water to it. Okay, so that you could shift it back this direction to reform the hydrate. So that's really all there is to what is a hydrate, what's an anhydrate, and the reaction that they undergo, which is dehydration. And so now let's talk about how we name hydrates, and then we'll do some math with them. Okay, so naming is actually relatively simple. To name a hydrate, you name the ionic part of the hydrate first, just like all the other things we name. So in number 1, MgSO4, that's magnesium sulfate. And then we use our covalent terms for our numbers. So 7 is the one that nobody can remember, which is hepta. And then we finish it with hydrate. And that's how you name a hydrate. So you name the ionic part, the prefix for the number that comes in front of the H2O. In this case, it's 7, so hepta. And then we finish it with hydrate. So in number 2, we name the ionic substance. So sodium sulfate. Okay, the prefix for 10 is deca. and then we finish it with hydrate. That's it. So sodium sulfate decahydrate. And then in 3, we name the ionic substance. Careful here because this is a transition metal. This is iron 2 sulfate. And then again, it's a 7, so heptahydrate. Okay, so that's naming. Very simple. And then as you can guess, going the reverse direction is just as easy. You write the formula for the ionic substance, and then you reference the prefix with the amount of H2Os. So calcium chloride, of course, +2 - 1, so CaCl2. Dihydrate, so we put the dot. That's just the way that they're written. Di means 2, so 2 H2Os. And then barium hydroxide, +2 - 1. Octa is 8, so dot 8 H2O. So there's how you could write formulas from hydrate names. It's just as simple as it sounds. Okay, so where we get into the math behind this is when we actually look at data from a dehydration reaction and then working backwards to attempt to verify the formula of that hydrate. So let's look at an example. We'll do 2, and that will be the end of this video. All right, so a calcium chloride hydrate has a mass of 4.72 grams. After heating, the mass of the anhydrate is found to be 3.56 grams. Determine the hydrate's formula. Okay, so we know it's calcium chloride. I know it's a hydrate, but I don't know this number, okay? And so that obviously here is the goal, is to figure out X. Let's talk about what X is for just a minute. So X is a ratio of how many water molecules there are to 1 calcium chloride, okay? So X could be 1, it could be 2, it could be any whole number up to 10, all right? So that's what we're trying to find here. So if we think about this, this is dehydration, so we would be left with the anhydrate plus however many waters there are. Okay, so from here, I need to figure out how I am going to solve this. Okay, so what do I know? I know the mass of the hydrate is 4.72 grams, so I know this is 4.72 grams. And that's great and maybe helpful. However, I don't know what X is, which means I really can't do much with this number in terms of like changing it to moles because I don't know what X is. But it's probably going to be helpful in a different respect. I do, however, know the mass of the anhydrate, which is 3.56. So that I could definitely calculate a mole value with. And then think about this for a minute. If I know the mass of the hydrate, the mass of the anhydrate, well, then the difference between them must be how much water was driven off. So that's a really good, that's a really good place to start, is to say, well, if my hydrate weighs this, and my anhydrate weighs that, the difference between the two must be the mass of the water that was evaporated. And so that's 1.16 grams. So then all of a sudden I have the mass of the anhydrate, the mass of the water. And again, remember, I'm looking for the ratio. So this is a great starting place. I have this mass, and I'm looking for the mole ratio. So I need to take those two numbers and change them into moles. So my 3.56 grams is just the calcium chloride, and my 1.16 grams is my H2O. And 110.98. Okay, so I do my math. We end up with 0.03208 moles of the calcium chloride, and we end up with 0.06439 moles of the water. You might be inclined to put these numbers here into a sequence, but I think you can, and I think though you're still going to question, well, what is X? How do I find X? So this is a little bit like empirical formula determination. It's been a long time since we did that, but when we're looking for the ratio in these numbers that maybe is not evident, remember the trick is to divide by the smallest. So this number is smaller. and we end up with 1 calcium chloride to 2 H2Os, okay? And so what that means is that X is equal to 2. So if X is equal to 2, then my formula is, I'm out of room, I'll come over here, is this. And this would be calcium chloride dihydrate. Okay, so that's how you can use the data in a problem or in a lab to backtrack and figure out the identity of your hydrate, okay, by finding X. So remember, the reason that this number here wasn't super helpful to me, other than to find the mass of the water, was because I didn't know X, and so if I don't know how many waters there are, then I cannot calculate this thing's molar mass. Okay, so while that number was helpful for me to find the water, I could not use it to do anything with moles here, and that's an important point. There's one more problem. If you would like to, I would recommend maybe pausing this, trying it on your own, because it's very similar to the last one. All right, so a 15.67 gram sample of a magnesium carbonate hydrate was heated to drive off the water. The mass was reduced to 7.58 grams. What's the formula of the hydrate? So I know it's magnesium carbonate. And again, I'm looking for X. I know we heat it, we drive off the water to make the anhydrate, and some number of water molecules. So again, same idea. This is the whole hydrate, and my 7.58 is what's left, which is the anhydrate. The difference between the two is going to give me the mass of the water. Hold on, I did not do this calculation ahead of time, so I'll have to do it as we're doing it. Okay, so we got 809 grams of the water. And again, I'm going to do a ratio of the water to the anhydrate to find X. So I know 7.58 was my anhydrate, and I know 8.09 was my water. um, 84.31. Do my math here. And that's my moles of the anhydrate. And my moles of the water. Significantly larger, okay, than the moles of the anhydrate. Keep that in mind. Remember, I mean, X could be 1, which means that the moles of these two would be equal. But other than that, the moles of the water always have to be larger, right? Because X is going to be a multiple 2, 3, 4, 5, so it's going to be bigger than the moles of your anhydrate. So keep that in mind to look for a mistake. Again, to find the hidden ratio divided by the smaller, which is, always, that's why I say this, always going to give you 1 mole of your anhydrate. If it doesn't work out that way, something's wrong. And then this comes out to be 5. So X here is 5. So here's my formula, and this would be a magnesium carbonate pentahydrate, and that is how you use dehydration data to backtrack and find the formula of a hydrate.